Good morning. Okay. Oh, record. Right. You recording? Okay. Cool. Sweet.
You're unmuted, right?
I am unmuted. Yes. All right. Fatigue. Woohoo! One more reminder: if you didn't last class, or you were gone, or for whatever reason, we're once again asking you to fill out the October feedback survey. So feel free to do that at some point soon. It's linked here and all that. So yeah, we have a lot to cover, so we're not going to do that right now. But if you haven't already, do it. Cool. All right. Lesson plan. What is fatigue? Oh, also, by the way, shout out to Katie who put together like 95% of the slide deck. A couple of us added a couple of things at the end, but mostly all Katie. So if she was here, she'd be presenting. But alas, she is getting ready to go to Paris for her fall break, which is rough. I don't know if she actually put any slides in here, but she also mentioned AJR concert in Milan, like on Monday, just because why not, you know? Just living life. Anyway, so what is fatigue? Types of fatigue, SN curves, symptoms examples, just kind of general, what is fatigue, what's going on there. How to determine fatigue life. We're not going super deep into the analysis. We're kind of giving you like the main, like this is kind of how you begin to look at fatigue analysis, because the actual real stuff is kind of hard. So, and I don't know, we'll get into it, but we're going to give you like the really fast version. And if you want to learn more, go read Shigley's, because it's a really actually a very good readable chapter. And then we're going to talk about how you can calculate fatigue life and build diagrams with steel in particular, and we'll give some examples. Yeah. What is fatigue? We're all feeling this a little right now, probably. Yeah. Especially like that one up there. This one's a big mood right there. Yeah. This is me a little bit last night. Yeah. Anyway, and you know, Jean-Luc Picard, can't go wrong. Okay, so this is a really scary case study. This is like one of the scariest things I've ever seen, ever, in terms of engineering. So, yeah, I'm not exactly sure what year this was, but it was like, I think it was like 70s or 80s, somewhere in there. And so there was a 737 flying over the Pacific, I believe it was. It was near enough to shore that they could get it down, but it was not like, you know, right over they were like at altitude. And all of a sudden, just a big chunk of the front part of the fuselage just whoop, flew away. And I don't know. If you want to know the gory details, you could look it up later. But I'm pretty sure people got, you know, ejected. I think like one person got ejected, and the rest were like belted in and were like okay, but like had a severe like wind shock and all this other stuff. Anyway, really scary. And basically, after a bunch of investigation, all that kind of stuff. But I mean, the plane actually landed shockingly, as you can see. So the big section left, like all the air masks dropped, but there was no like all the oxygen lines had been ripped out also. So the pilot had to like descend as fast as possible out of hypoxia region, which would have killed everybody. The pilot had to descend really fast without like ripping the plane in half, and then managed to set it down gently enough that it didn't break. And it's pretty crazy. Anyway, a lap joint between two plates of metal. You know, basically an airplane, right? It's a pressurized system. It's a pressurized tube. So every time it's pressurized and depressurized, it like pulls tension and then releases that tension, and it repeatedly. And that repeated loading caused fatigue cracking to occur along those lap joints in the metals. And so, yeah, what happened was that panel just got overpressurized, or like eventually, even though it should never have broken at that limit, it's way below its yield strength, right? It's when it was first manufactured, but because this crack started forming, explosive decompression occurred, and yeah, very scary. Another scary one was the Mississippi River Bridge collapse on I-35. This is Minnesota, I believe. And basically, this is why bridge inspections happen. Same thing, also why airplane inspections happen. This is why inspection happens on most material, like most metals that are used for really, really long duration in industry. It's just because of this. It's so like looking at these little flanges and gusseting plates right here. Because those are the parts of like a lot of the parts of the bridge just see like pure compression loading, and like the compression might vary a little bit, but it's not going to be like dramatic. But you know, when cars and semis and like big equipment is traveling across and they're like jostling the bridge, wiggling it, you know, stuff like this can see like cyclic loading, right? Like so it's oscillating the whole time. And so what happened was the gusset plates were a little bit undersized, which means that they were prone to fatigue much faster. than they should have been, and the plates cracked, and then the beams weren't connected anymore, and thus the bridge collapsed. So yeah, fatigue is real, and it's scary, and it is kind of hard to predict, and it matters a ton for really big stuff. That's the gist. But it also matters on small things. I'm pretty sure, like if you're here, you've probably done the paperclip bendy thing at some point. So like if somebody handed you a paperclip, how would you break it? Like, yeah, that right. Like you're not going to sit there like an instructor to go tunk and just pop the thing, like that'd be pretty entertaining, but I don't think I can't do that. I guess maybe if you didn't have leverage or something, but just with your bare hands, you're not going to be able to snap. You're not going to be able to exceed the ultimate strength, right, of that paperclip. So you're going to fatigue it. Like that's the easiest way to break something, and it's true a lot of times in with long-term used parts also. Yeah. So looking at the stress strain curve, so if you like parked the paper, if you like put the paperclip in an Instron or whatever, just hung a weight from it, and you just kept it right here, or even like right here, or you could just hang it there, and it would stay there. Like, theoretically, it would stay there pretty much indefinitely, right? Like it would never fall apart, and it would never break if you just parked it at even like just below the ultimate strength. If you just like parked it right there and just held a weight from it, it would theoretically never break. I'm sure there's probably some reason that it would eventually, but in a perfect world, right, assuming a spherical everything, it would never fail. However, if you travel up and down this curve over and over and over and over and over again, it will weaken the metal over time, and it'll break. An important thing about paper clips to note is that when you are bending them back and forth really quickly, and you're bending them like at a severe angle, you're not just passing the yield. I mean, you're going past the yield strength, right? Because if you like bend it all the way over and let go, it'll stay in that position. So that means you're passing the yield strength in bending. And so at that point, you are like going all the way up this curve and back down, and like probably not getting the ultimate strength, but you're like getting somewhere way up here, and then going back down. So it's like you're like going be over and over and over again, and that's what causes fatigue very quickly. Yeah. Okay, so the oscillation in that force, like for example, the paperclip is more like it's like bending forces, right? So it's tension on one side, compression on the other side, and like oscillates back and forth. But if you look at like kind of like if you're looking at a stress element on any one of those parts, it's going to look like the loading's going to look somewhat like this, right? That makes sense. So you can have, of course, you can have different types of loading, right? So like not everything in the if you're looking at like a car suspension, it's not going to have a perfect unless you're like riding in a rumble strip where it's like perfectly up and down. It's never, there's potholes, there's rocks, there's all sorts of different things. So it's never going to be a perfect sinusoidal wave. But this is kind of like the baseline that everything, all the engineering documents are built off of. This is kind of a sinusoid. So yeah, so fatigue failure is very common. A lot of places, I know there's lots of numbers on lots of different sites, but generally it's considered that like 90% of all failures in quote unquote real life are fatigue failures. And yeah, why do you guys think that is? Like, right? Why is it not more common to have like ultimate or yield failures?
Because like the design for fatigue is like time dependent and not so much like structure dependent.
Yeah, so like exactly. So it's like every industrial piece of machinery is like really overbuilt and has so much metal in there, but it's also used for like decades and decades, and all like like for like example, like a giant industrial like diesel engine, right? Like those parts are incredibly beefy. They're huge. It's never ever gonna get it's gonna be like down here somewhere. You're gonna have a huge safety margin for your yield strength, but over time, fatigue weakens that like effective strength of your part. Yeah.
All right, this is like super off, but like
yeah, go for it.
I was wondering, does this have an impact on if you're like, let's say you're recycling like a certain bit of aluminum for a really long period of time? Is this also affected?
Okay, so that's a very good point. If you remanufacture, if you like melt down a material and then re-refine it and then reprocess it, it resets fatigue, I believe, without exception. Because basically, we'll get into why fatigue happens on the next slide. Nice, and that should answer that question. Okay, yeah. So parts that are designed to run for a run for a really long time, or see really bad vibration loads like suspension components are often fatigue limited in their design. So they're not like, you're not just finding a safety factor for your ultimate or your yield strengths, you're finding a safety factor for your fatigue strength at a given time period. Yeah, which means that for example, for like a car suspension, like you could make a part way lighter if you didn't have to deal with fatigue, right? Because you could just remove as much of the material. You could be here always on the car suspension part. The problem is like that only may last like 15 laps of a racetrack, or it could be anything. Depends a ton on the loading, but like a lot of vibration and shock loads can go very quickly. Yeah. Also, it's a good point to check. Does everyone understand the difference between strength and stress? This one like always tripped me up until like 3 days ago, and then I'm like, oh, of course. Yeah.
Can you
yes. Yeah. So basically, strength is a limit of stress. So this is a plot of strength is the yield strength. So this is the amount of stress at which the part will yield, or that material will yield. So strength is just a limit of stress at some magical value where something happens. So in this case, it's yield. In that case, it's ultimate. And there's also fatigue strength as well. So that's the point at which it will break if you go any further. Yeah. Cool. Any questions? Yeah. Excellent question. We'll get to that too. No, not everything will always fail in fatigue, always. But most things are.
Like over time, is there anything that will not fail?
Yes. Yes. Okay. So what is fatigue? This is really, go take Matt Tsai. Like, this is stuff that I've read, and I also talked with Matt Neal about this once too. But basically, the way I understand it, which may not be perfect, but the way I understand it is these things called dislocations in the metal. So metal is made up of like a lattice of atoms, right? And different alloys have different lattice structures and all the rest. So metallurgy is not covered in this class. Go take Matt Tsai. But basically, there can be dislocations here where there's like a gap in the lattice structure, and what happens is even if you don't exceed the yield strength, even if you're like way down here, but you're like oscillating back and forth, it can give these dislocations a chance to kind of like slide through the lattice structure. So I don't know, there's some really good like videos of it online if you want to like look them up, look at like dislocations and things like that. It's what they're called. So yeah, you can watch videos. There's like good examples, like a bunch of ball bearings and like between two acrylic plates, and you can shake them and they kind of settle in an interesting way, and like little gaps like this in the pattern like move out to the edges. And the same thing happens in metal. So when you're bending this paperclip back and forth, even if you just like flick it back and forth a bunch and you're only staying below the yield strength, these dislocations will migrate towards the edge, and they will promote stress concentration. So like we saw with like a lot of the problems we did in the last couple of weeks with the stress elements and things like that, the majority, like generally, your peak stresses are likely to be at the edges of your part, at the surface, right? And so what can happen is if these kind of move to the surface, it can kind of create these weird voids and pockets and stress concentrations, so that like at that height, there's like a really sharp little point, even if it's not like full crack, it looks like a little sharp indent into your part. And then the next time it's loaded cyclically, like every little time it's cycled, the crack grows a little bit and grows a little bit until the majority of the rest of your part the stress is high enough, right? Because it's like load divided by area, right? So eventually the rest of your part can't take it and just snaps. And that's why fatigue happens suddenly. And the only way to foresee it is by finding these cracks, which is why bridge inspections and airplane inspections are done so frequently. Also, as a general rule, tension matters a lot more than compression. That makes sense. Why? Why might it be?
Your crack isn't like it's being closed up again, right?
Yeah, exactly. Yeah, so cracks are strong in compression-ish and non-existent in tension. So tensile, there are things that can fatigue in compression only, but it's much more important to worry about tension. So also because this process is so independent on the exact like sample of metal you have, fatigue is really hard to predict. Like you can't just like I don't know. It's much. It has a lot more variance than kind of the macro. Basically, this involves like the atomic lattice structure, right, of the part, which means that it varies a lot more between part to part than like the yield strength does. So like all of these measurements we've been talking about and material properties are all like statistical, but fatigue is even more statistical. There's even more variance between the different measurements of the same thing. So basically, like fatigue analysis is based a lot on testing, of course, like everything, and also usually has a wider safety factor depending on a lot of things. But yeah. Oh yeah, this is a great video, and we're gonna watch part of it, and I highly recommend you come back and finish it later if you are not like totally fine on fatigue and understand it better than I do, because I found this incredibly helpful.
Is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had fractured. The broken exercise equipment,
That would be
a torn
impressive.
blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is. Each day, thousands of items break due to cyclic, often repeated loading. How can we make sure that all these components withstand the cyclic loads? To achieve this, one has to test the materials appropriately. We intend to measure the fatigue strength of a frequently used steel in our laboratory. Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters.
It's a revolved dog bone. Wow.
The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with 2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts.
Could not have foreseen that.
The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The
Big
specimen
spring.
is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted, and there in turn, a mass.
Big spring.
An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact.
That's fast, but it's take a little while.
In reality, however, several cracks have already developed on the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the
See right there?
The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces.
Cautiously.
At first glance, the fracture surface looks unimpressive. A closer look, two regions, the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. We want to know how many load cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. The problem with materials is that...
There we go. They should really fix that. I don't know why it does that every single time. All right. Yeah, does that make sense to everybody? Kind of super cool. I love that, like magnetic or the mechanical resonance drive. It sounds like super sci-fi, but it's pretty cool. It's a big spring. Anyway, also the like kilonewtons, like lots of kilonewtons. That's like significant loading. That's kind of crazy. Yeah, super cool. Okay, so this is like, we'll talk about this more. We'll circle back to this, but SN curves are the big thing in fatigue, like the coolest thing. So basically, this is fatigue strength. So basically, the stress at which, like the amplitude of the stress. Remember from that sine wave. So this is the fatigue strength. This is the amplitude of the stress that you're applying, and this is the number of cycles. And the number of cycles is on a logarithmic scale, and that is very common because you got to pack like relatively small numbers up here, and you got to pack really, really large numbers on this side. Like 10 to the 8 cycles. That's like it's a lot of cycles. Yeah, so fatigue life is, there's a bunch of words that all are a little bit different depending on where you look, and they all mean the same thing though. So fatigue life, or this N number, N is usually refers to number of cycles, and sometimes it's N sub F, some other things like that. It's just the number of cycles, and then S sub F is the strength of fatigue strength, and that's in some strain or stress unit, not strain, stress unit. Yeah, and then failure occurs suddenly, because you're going from, basically the crack propagates until the rest of the material fails, like until the rest of the remaining cross-sectional area that is intact passes its ultimate strength. And then that's why when a fracture occurs, like we saw in that other video, the two pieces don't match back up perfectly together because there's plastic deformation that happens in that last fraction of a second before it pops. Yeah. So yeah, we'll circle back to this, but this is the kind of primary thing. And each one of these things is a data point from, like each one of these black dots is a data point from a test that is similar to what we just saw. So you can see there's quite a bit of, it's pretty well packed up here, and then it kind of spreads out as it goes. Yeah. Okay. So here's some more definitions. This is kind of like, I don't know, a lot of these slides, Katie made sure it was like super good for referencing later. So a lot of the stuff is just kind of like dense to look at in presentation mode, but if you go back later and you want to know what the stuff is, it's really handy. So yeah, basically cycles to failure, fatigue strength, we just talked about those. Does this make sense, everybody? We'll circle back more, but endurance fatigue limit. So this is a stress level below which a material can be said to have infinite life. So this is answering your question. We're going to answer it more specifically later. There's also low cycle fatigue, high cycle fatigue, and infinite life. So I don't buy that. I think I don't know. I don't buy that. I don't think this is always true. I think it's often true for particular materials, but I don't think it's always true. It's also not true in every situation either. So like helicopter parts, for example, they endure cyclic loading, I don't know, like hundreds or thousands of RPM. Engines too, hundreds of thousands of RPM for hundreds and thousands of hours. So then like that is a lot of cycles. And so you could get past this number relatively quickly. Basically, different industries and different load cases, different parts have different numbers of cycles they need to endure based on the loads they see. So infinite life can mean different things depending on different parts. But if it's more than this, it's probably not going to fail in the foreseeable future. But that's not good enough for like helicopters or airplanes, of course. Yeah, I'll talk about low and high cycle fatigue in a second here. Okay, so now we add some more labels. Low cycle fatigue is generally this like first region here. Also, the curves don't always look like this. And the curves also don't always have low cycle fatigue at all, because SN curves are really only like kind of accurate above like 10 to the 3 is like the general rule. I don't know. Fatigue is very hand wavy in general, but as a general rule, the low cycle section here is often just removed from a lot of plots that you see because it's not the important part, because in low cycle fatigue, it's actually plastic deformation. This is what's happening when you're bending the paperclip back and forth. So it's because, of course, you're not doing like thousands or millions or billions of cycles on the paperclip, right? You're just doing a couple of them. So you're plastically deforming that every single time. And so fatigue happens differently when it's like dramatic plastic deformation than when it, so you're below the ultimate, but you're way above the yield than when you're doing really high cycle stuff. So yeah, high cycle stuff is the primary stuff we're going to be focusing on, because as long as you have a good enough safety factor to your yield or ultimate, you're probably not going to be up here. You're probably going to be down here. If you're up here, you're I don't know what parts would be designed up there, actually. I don't know. Yeah. Any questions so far on this stuff? Cool. Okay, so here are the kind of 3 big methods that are most used probably. So stress life is the big one. So this is based on the stress levels only, and it's not accurate for low cycle fatigue when there's a lot of plastic deformation, but it is the most traditional method. It is like the kind of the go-to. It's definitely the easiest to implement. It can do it really quickly. There's a lot of supporting data for it, for different materials and all that kind of stuff. And it represents high cycle stuff pretty well. So anything that's like more than a couple, like in the thousands, more than the number, like thousands of cycles. And so that's like this stuff over here, right? So just like small oscillations causing cracks over long periods of time or long numbers of cycles. There's also strain life, which is kind of a more detailed look at plastic deformation in localized areas. So that's kind of like this, right? So like that's like, for example, for the paperclip, you're causing plastic deformation at that point. Yeah, so that's good for lower stuff. There's also some uncertainties here because, of course, it really depends on the exact piece that you're testing. So again, it's like a statistical and it's a large safety factor kind of way of looking at it. And then linear elastic fracture mechanics. This is like advanced computer simulation stuff that you combine with testing. So like, for example, this might be used on bridges where like a couple of cracks have appeared, but they're like a lot of time people like engineers can use this to define a critical crack length where as long as the crack is shorter than like 1/10 of an inch, it's fine. And then if it goes beyond 1/10 of an inch, it has to be repaired or the part has to be replaced based off of these predictions. So basically you can get away with a crack for a little while if the stakes are relatively low for a part, or if the part is just so massive and so overbuilt that you have a good enough amount of margin and you have done the analysis to show that it won't fail. So yeah. Cool. These are the big 3 main things. We're going to revisit some of them later. But yeah, again, look at Shigley's if you have more questions about specific things. Okay, so like we said before, this is what we were seeing in that laboratory test, right? So it was like a spinning mass on the end of a spring. So that spring is going to help you get this like sinusoidal pattern, right? So all of the SN curves, all of these are pretty much always going to be based off of sinusoidal loading and not based off of real world loading. So for example, like real world loading might look a lot more like this. So like there's like oscillatory changes in overall like average strength at any given time, but there also is probably like really small jitter at the same time. Also can be just not even sinusoidal at all. Like a lot of things aren't actually sinusoidal. Some things are, but the majority of things are like bumpy and shaky and different. And it's also just like stuff that's just all over the place. So yeah, just be aware that stuff is tested like this, and then the real world treats it like this. And so that's another reason you have to add even more buffer, because it's, there's no guarantee that this could be better or worse depending on what the actual amplitude is and what all the patterns are and things. So, but definitely less predictable. So great, more issues, lovely. Okay, so here's some cool symptoms of metal fatigue. This is kind of looking at the different parts. So stage 1 is initiation of the micro crack due to cyclic plastic deformation. That can also be just like really tiny local yielding also, and it's like it doesn't have to be macro yielding of the part, or like there doesn't have to be actual dramatic change in strain or anything like that. It can also happen at a local level, but for plastic deformation, this is true. And then it progresses to a micro crack, and then it opens and closes, and that's what causes those like striations, right? So every time the part's loaded, it like opens up, it like tears a little bit more, and then it's compressed again, and it tears a little bit more, and that oscillation is what causes these kind of stripes. So you can see the like, crack initially started there, and then it kind of cracked a little bit, and then it kind of got pulled and pulled and pulled and pulled. And then this area down here is that the remaining material is insufficient to carry the load, and it fails by simple ultimate failure. So pops. Woo! This is also in Shigley's. This is a very cool graph of like, basically this is like a way of looking at a part and telling what kind of failure happened to it, or where the fatigue was. So there's like, this is normal tension compression stuff. This is the kind of stuff that we were looking at in that test video. So that's just, back and forth tension compression. There's also a unidirectional bending test. We'll, I think there's a picture of what a test for that looks like later, but it's pure bending. It's not any tension or compression at all, or shear. It's just pure bending forces. There's also reverse bending. I don't know the difference. Great. Oh, actually, I do know the difference. Unidirectional bending is just, it gets bent and then it goes back to neutral, and bent and goes back to neutral. Reverse bending is it gets bent in both directions. If that makes sense. So there are differences. So like on the sine wave, that would mean it would go up and then flatten, up and then flatten, up and then flat, or it should be like sine wave above the axis. But the average stress would be different. I think the line is the same. Yeah. Yes, I see what you're saying. Yes. Yeah, so the mean stress is here, and it may be above the zero stress line. Yeah. Cool. Yeah, and then this is rotational bending. And there's a bunch of different things. And again, same kind of general thing. There are some questions about this in the homework, so be aware. Cool. Here's another example. Yeah, so basically same thing. This is a drive shaft of the keyway. So generally, basically the reason fatigue starts, it's always at stress concentrations, whether it's like a perfect like surface and there's just a small like surface imperfection on one side and that the crack propagates from there, or if it's an actual stress concentration like a keyway. Failure, crack propagation often starts at existing stress concentrations in the part. So yeah, again, the failure starts here, it propagates, and then it fails prettily way down there. Another example, this is a forged connecting rod. I'm not sure it's forged, it looks pretty cast, but whatever. It's not post-machine, that's for sure. Yeah, so in this case, the crack initiated at the flash line between the parts of the mold there. And then it propagated across, and you can see it didn't take very long because engines have high loads. So the crack got a little way, and then it just almost failed immediately because it had to get past the oil passageway, and then you lose this whole side of the I-beam in the oil passageway support, and then the rest of the material can't handle it, pops. Yeah. Cool. Oh yeah, it also got halfway around the hole, which is kind of interesting, the oil passageway. Okay, another thing. So this. I don't think there's actually, I've never seen a picture of the actual wheel, but this is from Shigley's also. But in this case, this like wheel cracked at the stamping marks because again, like it doesn't take a ton for cracks to form around like sharp corners and stuff. So even though these corners are like really, really tiny, it can still be enough to like propagate a fracture. So it's pretty interesting actually, like surface finish can play a role. So like a cast part versus a like ground or polished part can have different fatigue lives based on the surface finish. So an interesting thing to keep in mind. Okay, so this is a rule of thumb just to help your understanding. I've seen it a couple places, but it is not a thing to judge failure by any means, but it's just a general rule. So the rule of thumb, that's rough, is that a 10% increase or decrease in the alternating stress, like so the amplitude of the stress, leads to a threefold increase or decrease in fatigue life. So if you go from 100% loading, if you like drop it down by 10% to 90% of that loading, the part could last 3 times longer-ish. So that is basically just to illustrate that a small change in loading, or the same way, a slight increase in the amount of material on that part will allow the part to last way longer. And so if you like have a part and it's like under a lot of fatigue, so cyclic stress over and over and over again, you can add, if you add like 20% more material to it, roughly it'll last like 9 times longer in that situation. Again, this is very rough and those numbers don't actually mean anything. You got to actually do the analysis, but small changes in consistent amplitude of the stress matters a lot. And likewise, if you add a little material, it'll last a lot longer. Okay, so now we're going to look at determining fatigue life. Woohoo! All right. So like I said before, 3 ways: stress, strain, stress life, strain life, and then the fracture mechanics thing, which we're not going to really cover. We're going to look at a slide and it'll be like, ooh, that's cool. And we're going to move on. Again, look at Shigley's or talk to John Stoke or look into it yourself on ANSYS tutorials or whatever. But okay, so like I said before, stress life, traditional, easy, high cycle, within elastic deformation, no plastic deformation. And it is based on stress levels only. It's not accurate for low cycle, and there's a lot of supporting data. I don't know why that's a con. Anyway, this is important. We'll get to that in a minute. Okay, strain life. Like I said before, again, this is for plastic deformation, low cycle fatigue, and there's uncertainties in the results. That's true of everything, but there's like more uncertainty potentially in strain life. Yeah. Okay. Linear elastic fracture mechanics. Here it is. So Katie even didn't understand what this plot was. She just thought it looked kind of wild, and that kind of sums up linear elastic fracture mechanics as we understand it. I'm sure there's people on campus who know more, but have you looked at this at all, Colin? Great. Yeah. Yeah, basically, like I said before, it predicts crack growth. So this is for like if you inspect a structure with a, I don't know, like X-ray detection sensor or any kind of sensor that detects cracks, you can detect crack formation, and then you can build a computer model based off of that and predict when it's going to fail and how that crack can propagate. So the whole point is like cracks cause even more dramatic stress concentrations. And so if you have like a giant crack, it's not just like the strength of the material that's left behind. It's also how that crack continues moving through the lattice structure. So that's what this is all built around. Yeah. Okay, so testing. We saw one example, and that was axial fatigue. So it's just basically like if you had the instruments just go up and down and up and down and up and down for a really long time, which the instruments can't actually do because they don't do like compression with the normal jaws and stuff like that, and it would also take forever. So like having the oscillating mass means you can crank out those tests way, way, way faster. There's also high temperature testing. There's rotating beam testing, which I'll show a picture of in a minute, and there's also shear fatigue. So basically, shear can happen in pretty much any direction. Any stress can cause fatigue over time, but yeah. So here's the rotating test example. So instead of the other one, which is a front and back motion, this is there's a counterweight over here, and there's a motor, and the whole thing bends. And so the idea is to have no axial loading and no shear, but just pure bending of that part. And then you're rolling it over. So it's basically if you look at one spot on the test sample as it travels in a circle, it has tension on the top and compression on the bottom, and it alternates between that in a sine pattern, right? And so this is another way of getting at a similar thing, but it's a different load case. So depending on like if you're looking at a drive shaft in fatigue or like some kind of like a in link or something like that, you can have different types of fatigue. So this is a way of testing that. Yeah. That makes sense. Anybody have any questions also? Cool. Okay, stress life test method. Oh, right, so this is looking at the same thing. So basically this is also from Shigley's. This is kind of what the TANS sample might look like for the rotating thing. This just describes more about that test. Not gonna worry about it. SN curves, okay, this is more detail about that. Like we said before, it assumes this, not this, even though this is what's actually going to be in probably. Yes, only one component of loading at a time. So axial, torsional, bending, etc. Mostly used for high cycle stuff, and mostly elastic, which means the same thing basically. Okay, so we're going to talk about this more at the end, but the short answer for the what things can last forever question is steel's can last forever, and most ferrous materials can last forever. There's probably some exceptions to that. And then pretty much everything else will fail due to fatigue someday. It could be at like 10 to the 15 cycles or whatever, if it's like the strain is, if you're just like barely moving it at all. But anything that's not steel will fail at some point, or ferrous. So this SE thing is often it's the infinite loading thing. So it's the like the limit. Let's see. Yeah. So basically, if you take all those test samples from the testing, you plot it on this graph, you will form an SN curve. And you can put a line, generally SN curve lines. So these are just like made up lines, right? These are just fake. But most actual lines that you can look up and reference are based off of it's like literally just a line of best fit, which means that half of the parts they tested failed below that line. So if you put your part right on this line, it means that it has a 50% chance of failing like before. So that's something to keep in mind. Again, got to have a safety factor. Yes, and then for aluminum, copper, pretty much everything else that's not steel, it will eventually fail. But generally, like, again, this is before it was 10 to the 6, now it's 10 to the 8. Basically, depending on the industry and the part and the loading situation, it will change that value. And you will have different like functional infinite life limits. And because it's like a logarithmic scale, right? So like, for example, like airplane parts might be like here, helicopter parts might be here, and then like industrial equipment parts that last for 50 years might be like way up here or something. It just really depends on that particular part and how often it sees its cyclic load. Yeah. Yeah, we've covered this, I think. Yeah, basically, just be very aware of like what's high cycle and like where this flattens out. This is often called the knee. Yeah. Yeah, thanks, Katie. Yeah, so this is like a non-ferrous material. So like aluminum, copper, brass, pretty much everything. And then this is what it might look like for steel. So basically, like it's continuously, like it's almost like a limit, I think. I don't know. People don't really test past like 10 to the 8 because that would take literally forever. Yeah, steel is usually flatline about here. And as long as you stay below this strain in your oscillating loads, it will theoretically never fail. So if things have to last like forever, don't make them out of anything but steel, basically. But forever can mean different things, as we talked about. Yeah, also a really important thing, we'll talk about this again later, but like non-corrosive conditions and temperature and other things like that do matter. So if you like put a piece of steel in like an acid bath or like in salt water or whatever, it may not have the same property because like having contaminants outside or things that affect the strength of it, they can like crack, creep into the cracks and help like exacerbate fatigue sooner. So this is like true in like laboratory or like really clean environments, not necessarily true in the real world. So another issue there. Yes, and like I said, it's the median point, so it's 50% of expected failures, which means that your part might fail earlier. Yeah. Okay, I think we talked about this already, but paperclip, when you're bending it back and forth, you're in plastic deformation, so it's low cycle fatigue. You could do a paperclip experiment with high cycle fatigue, but it would take a long time because you have to like flick it and never plastically deform it, so it would take forever. Yeah. Okay, stress life. Also, we can take a break if people want to take a break. We've been here for a little while. If people want to like get up and stretch your legs a little bit. Yeah. All the homework for this should not be scary. It's going to be released. Well, I think it might be live now. I'm not sure if it's posted yet or not. But it should not be scary. Please do not like get stuck on this. It's like there's some things that might be confusing just because you don't know what slide to look at or how to do it, basically. So if that happens, don't like sit there for 3 hours trying to figure out why you can't figure it out. Like just come like email one of us or something. Yeah, it should be pretty quick. Good to go? Yeah.
Yeah, I have one thing. Is there anything in here about like an equivalent image model? I've heard that terminology used. Yeah, I've heard that terminology used to describe like.
Yes. I don't think we put anything here about it. Oh, that really is there, isn't it? Yeah, apparently, okay. Sidetrack. Apparently NASA made a supersonic propeller at one point. They took a jet in the 60s and they slapped a turboprop on the front of it and they made a super thin, super flat airfoil prop. And then they flew like at Mach 1.1 with a propeller spinning. So anyway, kind of wild. But somehow they like, yeah, I don't understand. It's, yeah, anyway, wild. Yeah, I don't think we have anything in this deck about it, but that definitely is a thing. Yeah, I saw it in a couple papers I was reading, and yeah, I don't know. We don't have anything formally, but we can look into it if we come to office hours, whatever, and we can chat about it.
Yeah, I think I had just heard of it being relevant in like interviews. They might ask like, "Oh, how do you go about testing something for fatigue or whatever?" And you could say, "Oh, I'd use an FN for like."
Yeah. Interesting. Yeah, I can dig into that, and I can send an announcement if I find anything super interesting about it. We'll put that into the list. Cool. All right. Everybody good to go? Shake off the early morning Monday. Is it Monday? No, it's Thursday. Wow. Yeah, that checks out. All right. Cool. We're almost there. All right. So yes, these are mostly for reference. We're going to go through it quickly. Yeah. Only applicable for completely reverse stresses. I'm not sure that's always true. I think there are ways you can use it for non-reverse stresses, so like non-fully reciprocating ones, but there's some caveats to that. Okay, calculating fatigue strength. Okay, so there's a lot of words here. We're not going to go through the whole thing. Come back and look at it later if you want. SN curve. Woohoo. So basically, what all this says is that one way of comparing your part, or one way of looking at the fatigue of your part is by literally just comparing it where you want to be on this plot. So looking at the amplitude of your stress from whatever your load case is, and then going over until you find this point, and looking down at the number of cycles, and then this equation functionally shows you where you are and like where your part is in relation to what has been tested previously. If that makes sense. Yeah, so the first way that you can check is just by literally, if you have an SN curve that is published and that you can reference as for your analysis, that is like, you know, so because sometimes you can't reference SN curves for your analysis for various reasons, but in this case, you just like go over, go down, and then find your thing, and that gives you a number. And then I'm not sure we ever settled on what eta actually is in this case, but eta is like, it's either like safety factor or something. I don't know. We don't fully understand this. Woohoo.
What is? Can you explain those numbers one more time? Because SF is
So,
number.
oh my gosh, wrong button. SF is the fatigue strength.
Okay.
So SF is fatigue strength. N is the number of cycles. So that's on these plots, right? So this is the vertical axis. This is the horizontal axis. Sigma A.
That's a product of the two, or is it saying the fatigue strength at a certain number?
I think it's the fatigue strength at a certain number in this case. Yeah, that's why I don't love this notation. It's just confusing for no reason.
And then sigma is.
Sigma is your load, I believe.
Gotcha.
And this gives you like your safety factor between those two, I think is what it's saying. Yeah, also, as always, it assumes ideal everything, of course, so real world stuff's gonna be below that. We'll get to like how you account for that later. Okay, so this is kind of like the first easiest way for steels to do this. Generally, steel endurance limit has been experimentally found related to the ultimate strength. So basically at the bottom is the ultimate tensile strength, and on the Y is the endurance limit, or the endurance limit is the same thing as fatigue limit is the same thing as like any combination of endurance, fatigue, limit, and strength are all basically the same thing. So endurance limit is the same thing as fatigue strength. So it's just S sub F, I think. So basically, These are all data points again, and you can see there's a lot of variance, right? But like the average general rule is that the endurance limit is 1/2 of the tensile strength. I don't know what, maybe endurance limit is actually different. Now that I'm thinking about it. Maybe I don't understand this. Colin, do you know? Endurance limit versus endurance or fatigue strength? Because this would have to be at one particular, hold on. Quick check. I might be telling something you totally wrong. Oh, right. Endurance limit is the, oh my gosh, right. Okay, sorry, my bad. Endurance limit is the point at which steels no longer have any, it's the infinite life point. So this is the point at which it has infinite life. So this is the strength of the material at 10 bajillion gazillion cycles. Yeah, so erase what I was saying about them being the same. It's not the same thing. This is just the, it's the equivalent strength at like infinite cycles, basically. So when that line goes down to flat, it's that height of that line. And this is the ultimate tensile strength. So generally, it's about 1/2. That makes sense. So for basically, it's actually think of the next slide. Whoop. Go back to the other thing. There we go. All right, back on track. Maybe. Aha. Okay. This is important. You use this on your homework. This is a rough way of estimating it for steels. So basically for ultimate strengths that are below 200 kpsi, generally the endurance limit or the fatigue strength at infinite cycles for steels is roughly 1/2 of the ultimate strength. Again, roughly. It can be up to 0.6, it can be down to 0.4 or even worse, and they're better depending on a lot of different things. So each one of these things is all different material, basically. There's all different types of steels and irons and things. So below 200 KSI or KPSI, it's generally about 1/2. If you go above that, it's kind of flatlines. Again, there's a big spread here, right? Like it's a huge amount of variation, but as a general rule, it's 1/2 until you get to 200 KPSI on the x-axis, and then it goes straight across to 100. So again, it's not like a great model, right? But it is a model. Yeah, I think this is just the equivalent metric. I don't think the difference. Yeah, cool. Does this make sense? Cool. Okay, this is like the derivation, also in Shigley's. I don't think we're going to go super far into this because I don't really want to. Basically, there's a couple different equations you can use to relate different things, and this is all building towards a model that I think is on one of the next couple slides. But yeah, basically, E is Young's modulus. This is your change in strain. So this is the strain method, I guess. So this is your change in strain. This is your Young's modulus. This is your fatigue stress, I guess. I don't know. I believe so. Number of cycles. This B constant thing is, you can calculate that. I think it's on the next slide. Basically, you start, this is the strain one. So you start with strain amplitude versus reversal. So this is your SN curve. You start with that. You define the specimen fatigue strength at the specific number of cycles. So you basically have this number of cycles you want to hit. You find the fatigue strength of that. You combine those two into one equation, and then this will give you a generalized form. So for example, to fill this out, basically, 10 to the 3 cycles. So you just kind of plug that into the previous equation, and then F here, this weird swooshy F, is the fraction of ultimate strength represented by. It's the fraction of ultimate strength that is fatigue strength. So it basically, this is your like knockdown value. So if your ultimate strength is, 200, like you were saying before, and this F, if the F is 0.5, your fracture strength or your fatigue strength will be at 100. So this is like a value from 0 to 1 that determines how much of the ultimate strength is what your current strength is at that number of cycles. again, feel free to just come dig through these slides later and come to office hours and we can talk about it more. But and then this is how you can find that B constant down there. So you're basically just substituting all these equations in to find this value. Yeah. Okay, so this is a plot of that value F compared to the ultimate strength, ultimate tensile strength of different materials. So this is like the general trajectory of, yeah. So it's fatigue strength fraction versus the ultimate tensile strength. Yeah. And this is assuming that thing we assumed earlier of that 1/2 value at 10 to the 6 cycles. So, yeah. So this is at 10 to the 3rd cycles. Wait. I'm confused again. Right. Okay, yeah. Okay, so this is, I'm not sure this is on homework or not. I actually think it is. Basically, you can write an equation for an SN line. So this one in particular, so not the low cycle and not the infinite life, but the one in between, which is the one you care about most of the time. If you're fatigue limited and you're not in this like bottom regime down here where you have infinite life, if you're in this middle regime, which is the most common one you're in for failure, you need at least 2 known points. And basically you're just making a line of best fit there. And because it's not linear actually, because of course it's a logarithmic scale, right? So even though it looks linear, it's not actually linear. It's actually like a really large dramatic swoosh. So hence this equation being not y equal to x plus b. Yeah, it's a log function basically. And so you can use these equations for your line. So this is your function here, and you can use these to these basically give you a and your b values, and then that'll give you a closed form solution. Well, it'll give you a way to estimate the slope of this line, so you can look at any other point and value it. You never actually want to do this for 2 known points. Like you never want to just test 2 samples and put a lot of line, because one sample might be like here, and the other one's like here, and you have a really warped perspective of what that line looks like. So you always want to do like a lot of averages, like you use a lot of points to define this. But this is a really fast way if you just have 2 data points to look at it. Yeah. Yeah, any questions? I know this is kind of a little bit unsatisfactory. Fatigue is wild, hard to predict. Cool. All right. It's the same, yeah. This is just another form of that previous equation, I believe. Oh yeah, so yeah, so this is what you can use that for. So if you find these values, this output, this is like another version of that, right? That gives you the same. So this will give you a number of solutions given a particular reversing stress. So this is the amplitude of that sine wave. Remember, the amplitude is only the height of one side of it. It's not the height of both sides. It's, yeah. Yeah, and this is for completely reverse stress, like we said before. Cool. Okay, so here's like, again, this is also on your homework, I think. So the Basquin equation, and I don't think we used the Kaufman-Manson on the thing, but Basquin is definitely on the homework, and that's basically Basquin is kind of this first part here, and sorry, Basquin is the second part. Kaufman-Mason is more of an estimation of that kind of earlier cycle stuff, and Basquin is like the main one that we've been looking at, and that's this equation here. And so that basically what we just saw is a derivation of the Basquin equation. So this is big. This is on homework. Know this. It was originally published in 1910 too, which is kind of wild. Apparently, I was reading that apparently railway stuff was the first time that they really came, people really came into fatigue and understanding fatigue. It probably happened on steam engines too before that, but like railway stuff sees a lot more cycles because every rotation the axles see. So like axles are breaking well below the calculated yield stress, and they were like, I don't know why. And so hence people looked into it and found this. And this stuff happened a long time ago, but it's still like the easiest, fast way of estimating it besides computer modeling stuff. Also, there's a combined version up here. I don't know about that. Yeah, you should know that you're in the right area probably, but yeah. Okay, endurance limit modifiers. These are things that you can put on your, basically a bunch of variables that you can put on your thing. These are all findable in lookup tables. I'm sure there's some in Shigley's and other places. But basically they are factors. They're basically between 0 and 1, and you slap a coefficient on it, and it knocks down your strength. And this is like a way of, it's a way of referencing other testing, other experience to inform your safety factor, basically. So basically you like take the calculated one that you found, the calculated endurance strength, or the calculated fatigue strength that you calculated. I said that way too many times. And then you can apply one of these offset values to it, and you apply a bunch of them. You can stack them. You know, given like a higher temperature, you need more reliability. You know, you have like some weird environmental factors going on, and you know your load is a certain size, and the part's a certain size, and all the things, these things you can look up in tables, and it really depends on the use case. So again, like if you're ever working at a company, they will help you be able to find this information, however that works. Yeah, there's also different ones based off of rotating bench stress, of like actual service conditions. So yeah, so sorry, the S sub E is based off the actual service conditions, and that's with all these modifiers. And this is where you might account for the difference between like the sine wave and that weird jittery wave. And the S prime and E prime this is based off that pure lab experiment. So this is the SN curve, and these are all knockdowns that get you closer to what your actual service condition might look like. Yeah.
Okay. So I know we've been talking about things, basically saying that it's really hard to talk about fatigue in the context of Olin, because usually we're not making things that are used maybe more than once, or maybe not used at all. So I'm trying to hopefully ground the conversation a little bit and give an example of kind of like a fatigue failure that we had in Formula. It was kind of obvious that when you look at it in retrospect, and hopefully you'll share kind of that obvious nature as I go through it. But just to give context of kind of the system that I'm talking about. So this example, we were focusing on the anti-roll bar. The anti-roll bar is kind of the system that goes in between my two suspension systems and acts as a torsion spring that I'm kind of bending and twisting as I move my suspension system. So normally when I don't have a anti-roll bar, or sometimes called a sway bar, or you might hear, I forget, there's like a bunch of other different terms for like automotive industry, I have independent movement of my suspension system, and that generally leads to then one wheel taking a huge amount of the load, and then this like other tire on the inside not being loaded as heavily. Conversely, like when I have an anti-roll bar, I'm kind of like sharing that load, and I'm using that spring to share it in between it. And then on your car, you have like usually a tunable anti-roll bar. So I can kind of change how much load is being shared and make it kind of adjust to what I need. So as I kind of think then, when I'm in kind of the context of a car itself, I'm going to start thinking, well, this is probably high cyclic loading. If I'm doing any given turn, that's one cycle. And generally you'll see like in the automotive industry, it's like 10 to the 6 or higher is kind of the number of cycles that we're dealing with. So you would think fatigue and kind of cyclic loading is something I should consider and should really be part of my design. And it really wasn't. So for context, the system that we designed basically had this moment arm. So this is kind of a cross-section view right now. I'll show a view of it actually in CAD later on that'll help explain things. But how we found out this failure is kind of after the fact, where we had this weld bead totally fail. And this is both a fatigue failure and also just poor manufacturing as well. Like you can see that it's really terrible, what is it called? Penetration for my weld itself. Like it was barely there, really thin wall tubing. And as we know from looking at the previous slides, aluminum is really not that great when it comes to actual fatigue loading. I mean, it was great for getting the right spring constant for what we needed for the design, but obviously my abstracted kind of idealized system is not true to reality and it's not useful if it breaks. And I will say, like contextually, like we were very lucky that it failed and like the person was not going fast or going in straight direction and could have crashed. You know, this was a pretty catastrophic failure where basically like this broke on our suspension system, and then by doing so, shock loaded our shock and like sheared basically our push rod, which like in I guess the simple terms means that our wheel was defunct and like you just like started skidding across the ground. So very lucky again, and really could have been avoided if we had thought about things. So for the actual system, this is where it actually is on the car. So you can see that we are using kind of like fully reverse loading, as we were saying before. So as I go into one turn, it maybe go up as like, say like this wheel is being loaded up. And then conversely, like as the other like right wheel might be going up, then it's going to be going down. So like, and then I guess like a worse loading condition, maybe I'd be in like a figure eight. And in the case that actually made this fail, we were going in circles continually in the same direction, which basically meant that like we were going like clockwise and counterclockwise and kind of like loading it constantly, and actually putting like the max torque on this moment arm that is applying on my spring. And I did analysis for the FEA class, where I was kind of looking at the actual kind of fatigue strength. So this is using the stress life method of determining fatigue strength. And there are great limitations to this analysis, mainly that these kind of models for materials are really contextual usually, and you need to find it for kind of testing in-house. So this is using ANSYS existing models. It is not necessarily the exact kind of material that we did use, but did give kind of an order of magnitude when it comes to kind of understanding where this happened and how it could have been avoided. So this is looking at kind of the weld bead that I was touching on before. And based upon kind of this model, I could see that really my weakest point is exactly on that weld bead when I start transitioning to my moment arm. And I can see that failure is occurring at 10 to like, I guess what is the 10 to the 4th. And I wanted to see like 10 to the 6th or higher. And basically using like really handshaky math, where if we look at kind of the number of cycles here on the low end for aluminum, which is what we actually used, that equates to about like roughly like 14 races when it comes to like the formula competition. And then looking at kind of past competition data, it's like 7 hours of driving continuously, which like is the same order of magnitude of when this actually failed on the car. But the long and short of it is that I really need to think about design when it comes to things beyond my static analysis. Like, sure, this part is not going to fail for max torque as I'm bending it once, but that's not the conditions that are realistic to what I'm actually doing. And I need to think about kind of connecting this abstraction of my system to, you know, something that makes sense for the manufacturing of it, that makes sense for how I'm actually welding this piece, and making sure that I'm not assuming like a purely bonded connection in my FEA analysis, which is not accurate if I have poor penetration on my weld. Obviously, again, like we got lucky that like no one got seriously hurt, but this could have really like caused like someone to crash into a wall or get seriously injured. So like these do have, I guess, actual implications to your own designs. You may find that this is really important for maybe a future scope or ADE project, or, you know, other classes. So just keep it in mind. This is, again, something that is definitely considered an industry, but still can affect you even in the context of Olin. And then another example that I thought of that I didn't put in the slides, but Nathan was mentioning kind of like these ideas of crack propagation. Like you'll see, and especially casted materials, that is a huge thing. Like when I was working at Haas, like one of the big things that they avoided like the plague is the idea of like microporosity in casted materials, and the idea that there are just these tiny bubbles that are inside my casted materials, and that will allow cracks to propagate from the inside out, and it will kind of like fail in a way where I can't even see that it's happening because it's not failing from the inside. And that will deal like with a giant, like thousands of pounds, like piece of casted steel basically cracking, and like maybe my entire machine tool like comes in half or something crazy like that. And I could see that on a machine tool, like this spinning thing that is kind of vibrating my machine constantly, that fatigue would really matter, and that I probably should think about how many cycles, given that it's spinning at like tens of thousands of RPM, and I'm moving it at a rate that is kind of using it constantly day in, day out. But yeah, if you guys have other questions about kind of like how maybe to use like the really simple ANSYS or SolidWorks fatigue models, let me know. I have like limited experience with it, but they are out there, and you do have some options when it comes to doing analysis at all. But yeah.
All right, we are about there. Thank you, Colin. Yeah, it's really cool actually. One quick touch on non-ferrous metals. Again, a lot of things, but yeah, a lot of words. Come back and look at it later if you want. Generally for aluminum alloys and copper alloys and things like that, 10 to the 8 cycles is like, if 10 to the 6 is fine for cars, like 10 to the 8 is, again, like orders like 2 orders of magnitude more than that. So this is like only for things that are like super high vibration or super aggressive things would pass this, would pass 10 to the 8. So generally this can be assumed to be pretty much the limit for other things. So this is just some more examples of that. Yeah. So this is an example of different types of a material. So like, for example, there's like, I don't know if there's anything but wrought iron. I've never heard of anything that's referred to as wrought except iron, but this seems to kind of have a little bit of a limit. So wrought iron would be, and then, again, like permanent mold cast is like die cast could be here, and solid cast could be lower. So this is again looking at like surface conditions, and the method of manufacturing can have a big effect, like Colin was just saying, with porosity and things like that. Sand cast obviously is going to be the roughest surface finish. It's going to have a lot of pores, so it can easily cause stress concentrations and cracks to form. Permanent mold cast is going to be smoother, and then wrought or polished or anything that's going to be higher than that. So this is an example of that in the knockdown thing. Okay, here is the kind of like another big takeaway. Generally, this is, again, the numbers maybe specifically aren't necessarily correct. This is again looking at like the kind of overall thing. So ferrous or steels and irons and things like that generally kind of have a shape that looks kind of like this. Aluminum generally kind of has a shape that looks like this, and eventually will go down to 0 given enough time. Yeah. So aluminum's not as good for fatigue. Basically anything, steel is the best for fatigue, pretty much, period. Other things can be totally fine, and like airplanes and helicopters are made almost entirely out of aluminum, so it's not like they, if you design your parts correctly and you take this into account correctly and you do correct analysis, it's totally fine to use aluminum stuff. But if you need something to last for, let's just run in a hole in the ground pumping oil for 10,000 years or whatever, steel is probably gonna be the right choice, generally speaking. Yeah. Okay, to close out, thought question for you guys to think about. Fatigue with other materials, composites, plastics. How might composites be different than normal isotropic materials in terms of fatigue? Any thoughts?
I feel like the resin might fail for the fibers.
Interesting. Yeah. There's some cool papers on this. Definitely, I'll throw some into the slides later, probably. Yeah, any other thoughts on that? I can talk a little bit about what I found, but yeah.
Actually, I think under torsion, I think maybe the failure would be a little different, because I know when people do carbon fiber prop shafts, those tear.
Oh yeah, those are crazy. Yeah, so there's a bunch of, obviously fatigue matters a lot for airplanes. Not failing matters a lot for airplanes in general. And composites also are a big thing in airplanes. There's a lot of papers that were looking at composites and things. So I just skimmed a couple of them real fast. But the general gist is that composites, kind of what we were talking about earlier with the damage model, this is where I saw that, the comparative damage model thing. Basically, the composites see more damage faster, but then it levels off for a while and then it goes back up again. And because what's happening is under cyclic loading, basically there's always boundaries between the fibers and the resin. And when those boundaries are flexed over and over and over again, they can micro cracks can form in the epoxy, like you guys were saying. And the fibers can kind of pull away a little bit, but then once it gets into kind of like a little bit looser state, it can stay there for longer. So depending on the type, I mean, again, composites like are so variable, way more variable even than the metals and isotropic materials, because it matters so much exactly how you lay it up and making sure that your fabric is really clean ahead of time so you get a good bond. There's so many more variables that go into producing it, because it's a handmade process, not a like a casting process or whatever. And so like really good, like pre-preg, really good aircraft composites can have a better fatigue life than steels or aluminums. But it's not always true, like I said, depending on a lot of different factors with the manufacturing. So yeah, but it's actually like you said, like the layers between, like it's not often the actual fibers don't have fatigue. It's the like combination with the resin, like the boundary layers between that kind of get damaged. And then plastics are a whole other thing. Fatigue does happen in plastics, but it's a little bit different. It's more similar to the way it happens in metals, but a little different from what I understood. Yeah, again, go talk to somebody about MatSci for that. But yeah, and then as always, we have a bunch of other resources that are kind of handy if you want to learn more about this. Yeah, and then just one other reminder, there's a reference resource check-in due tonight. So just making sure you guys are able to, like, giving you a good excuse to continually update that. So you don't have to do it all at the end. And yeah, again, this is for you, not for us. So we're just helping to prompt you to update your toolkit. Yeah.
And for homework 5 should be posted now. It's not due for a couple classes because we still have to talk about wear, obviously. And then we will have a class on shaft loading, but that won't be in the homework. And then I think the one after that will be when we have the universal exec come talk to us about kind of safety and engineering. And then what was it?
Yeah.
Oh no, sorry. I looked it up. Like wrought materials, just for clarification, are just mean like worked materials.
Interesting.
So it means like if I have an ingot and then I reheat it and then I reshape it, that's just a wrought material.
Huh.
Versus on, I guess, like the other side, cast materials, it's like I melt it and then I put it into the shape, and then that is kind of the final form. So basically, like having an intermediate step where I have ingots and I
Interesting.
kind of malleable kind of or ductile material that I'm pushing it into.
Huh. There you go. Ooh, okay. I have another fun video. If nobody else has anything that we want to talk about, I have a fun video that shows a little bit about grain structure that we can watch for the rest of the class. If that sounds good. No. All right. Woohoo! Thanks for hanging in there. I know this is like kind of a lot of just stuff. Yeah, it's cool. Fatigue is wild. It matters a lot. All right. This is also linked in one of the videos that was linked. Okay. Boop. Oh, I gotta unmute it. Whoa. In like 80s TV stuff. Hold on. Whoa. It's gonna be really loud or really quiet. There we go.
The safety barriers around this junction are coated with a thin layer of zinc.
The British really know how to make videos about this stuff.
If we look closely at the surface of the zinc, we see it's built up of many different patches. You can find this effect on a number of zinc-coated objects. The patches you see are crystals or grains of zinc. Here's a piece of a different metal. It's been machined along one edge. You can't see any grains in this surface. However, if we turn it over, it's quite a different story. This piece of metal has been broken in half. Along the broken edge, you can see some of the grains from which this material is made. All metals are made up of grains, although you'll rarely see them like this. In fact, with most metals, including this piece of aluminium, the grains aren't visible, not even on the surface. Here's a way of making them visible. First, we must give the aluminium a mirror-like finish.
You can do this in MatSci.
And there we are. And next, we treat the carefully prepared surface with a very powerful acid. Gloves are essential for this operation. As soon as the acids have time to react, the metal must be washed. It's then given a second treatment with another special chemical. We call this process etching. The particular chemicals used depend on the metal we're trying to etch. One final wash, and there are the grains. Grains of pure aluminium. They're all similar, both in size and in structure. They appear as different shades only because of the way they reflect the light. By etching, we can reveal the grain structure of any metal. Here's a different sample of aluminium. In this case, the grains are much larger and they vary in size. And here's a piece of copper. In this sample, the grains seem to get smaller as you get nearer the middle. Zinc, a sample whose grains are all shapes and sizes. But how do grains form? To find out, we've gone back to the stage when a metal is molten. In this furnace, the metal is aluminium. When the time is right, the furnace is tapped. The molten metal runs out into molds to form huge slabs of aluminium. In turn, the solid slabs will be rolled into sheets. From time to time, a small sample of the molten aluminium is taken for analysis.
I'm trying to visit a place like that.
The metal is almost as solidified.
Look how much it sinks when it cools.
Now we can see what happens as the aluminium solidifies in a special film. At a number of points in the liquid metal, tiny crystals begin to form and grow. Each crystal grows outwards in all directions until it meets the surfaces of its neighboring crystals. In engineering terms, each fully grown crystal is called a grain. In this piece of solid aluminium, there's a very large number of grains. Now, once the aluminium's been cast into slabs, it's rolled into sheets. To get the metal down to this thickness, it's been rolled many times. It's now relatively cold, so as the metal is squashed between the rollers, it's being cold worked. Let's find out what effect the cold working has on the grain structure of the aluminium. Here we're etching a piece of the aluminium before cold working. At this stage, the grains are all approximately the same size and the same shape. Remember, they appear different shades only because of the way they reflect the light. Now we'll cold roll a similar piece of the same aluminium.
There's one of these machines in the Mass High Lab too.
In one pass, this machine will reduce the thickness by only a very small amount. So we'll reduce the gap between the rollers and put the metal through again. Right, let's see what that's done to the grain structure. The cold rolled piece of metal is the one at the top. Can you see the difference? We seem to have changed the shape of the grains. They've become elongated. We can get a better idea of what's happened in a diagram. First, we'll look at the grain structure of the metal before it's deformed. Here, the grains are normal. But as the metal is squashed between the rollers, you can see how the grains become elongated and distorted in the direction of rolling. The change in grain structure that results from cold working is accompanied by a change in the mechanical properties of the metal. Its hardness and tensile strength increases while the ductility decreases.
Just like
After
paperclip.
cold working a metal, it's usually heated to a sufficiently high temperature. Let's see what effect heating has on the distorted grain structure. In the case of this particular metal, nothing happens until the temperature reaches about 350 degrees centigrade. Now, at the grain boundaries, new grains begin to form. These grow rapidly until a new, undistorted grain structure completely replaces the old, distorted one. We call this process recrystallization. Now, let's see what effect this has had on the mechanical properties of the aluminium. Hardness, for example. Here we're measuring the resistance to indentation of a piece of cold-worked aluminium. How does this compare with the size of the dent produced in a piece of recrystallized aluminium? It's much deeper, so recrystallization has restored softness. And what about the tensile strength? First, the cold-worked aluminium.
Inch-drawn before inch-drawn.
That needs a force of about 7 units to pull it apart. Now for a recrystallized piece. The force is going to be much less this time. The tensile strength has decreased. If we put the broken bits back together again, we find the recrystallized piece stretched the most. So we've also restored the ductility.
This is why heat treating is like the big thing in metallurgy.
However, the resulting properties depend on the temperature at which recrystallization is carried out. If the temperature becomes too high, some of the grains will grow at the expense of their neighbors. This can give rise to properties which are highly undesirable for most engineering applications.
Oh yeah.
This is molten steel. When it cools, it will solidify and grains will be formed. Let's find out what the grain structure of a piece of plain carbon steel is like. We've given this piece of steel a mirror-like finish. Now we're etching it.
Just like, ah.
The steel contains 0.4% carbon. So far, so good, but with the unaided eye, we can't see any grains. We'll have to take a small sample of the steel and view its surface through a microscope. Here it is, magnified nearly 250 times. Let's take a closer look at this in a diagram. In the case of steel, there are two different types of grains. We'll look at each in turn. The light grains, like this one, are made up of iron. Engineers call them ferrite. These give steel the property of ductility. The other grains, like this one, are made up in layers. The white layers are iron. The black layers are a chemical compound of iron and carbon, called iron carbide.
Whoa.
Perlite is the name given to this type of grain. They give steel the properties of hardness and strength. This particular piece of steel is made up of roughly equal numbers of the two types of grains. So far, we've only looked at 0.4% carbon steel. However, steel can be produced with other carbon contents. What effect does this have on the grain structure? We'll start with 0.4% carbon And let's add some more. Can you see what's happening? The number of perlite grains is increasing. Now there are no ferrite grains at all. The steel now contains 0.8% carbon. Under the microscope, a similar piece of like this.
It's crazy, isn't it? So
You can probably guess what will happen if we now reduce the amount of carbon in the steel. The number of perlite grains decreases, leaving a lot of ferrite grains.
I love that's shaky the whole time.
Now there's only
Couldn't
about
make a diagram,
0.1% carbon left. This is what a similar piece of carbon steel looks like under the microscope. Now we can change the mechanical properties of plain carbon steel by a carefully controlled sequence of heating and cooling by heat treatment.
Whoa. Also, feel free to
Let's
head out
find out
whenever.
what effect heat treatment has on the grain structure of the steel. The rings we're treating contain